A very pleasant good morning, one and all present here. Look here, I have succeeded at last in fetching some gold. I am Shara from Department of Chemistry on behalf of Career Point University, Kota, Rajasthan. Greet you all. We all assemble here to attend a webinar on spectroscopy technique and application. And today's keynote speaker is Dr. Neeta Azad of University of Delhi. Spectroscopy is an era of always a new world. It always an era of mystery. Spectroscopy is the study of interaction between the matter and electromagnetic radiation. Techniques that employ the electromagnetic radiation are typically classified by the wavelength of reason of the spectra and include microwave, terahertz, infrared, near the infrared, ultraviolet, visible, X-ray, and gamma spectroscopy. Spectroscopy finds a widespread in daily life. This concept is expanded greatly for determination of unique spectra of atoms and molecules to detect, identify, and qualify the information about them. It is used in analytical chemistry, photochemistry, plant chemistry, biological analysis, healthcare, medicine, astronomy, and remote sensing on Earth. Further, these techniques are easily integrated in other means of estimation and analysis like chromatography, elemental analysis. To welcome you all, I would like to invite Honorable Pro Vice Chancellor Dr. Gurudat Kakkar, sir. Over to you, sir.
Thank you. First of all, congratulations to the School of Basic and Applied Science and Department of Chemistry for organizing this expert lecture. Professor Azad is an authority in this area, and I am very much sure that the session will be very much fruitful for the students, especially in order to gain knowledge in the upcoming concepts and the modern technologies. This is, I'm not from the field basically, but whatsoever I have learned a little, this technique is somewhere very much relevant as and when some scholars comes to me and they normally demand for uh, this particular instrument for the purpose of their research and all. So I can understand the importance of it, though as I mentioned that I'm not from the field. I, on the behalf of Carrot University, welcome Professor Azad, and I'm highly thankful for sparing time in order to share the knowledge. I'm also uh, uh, I also welcome all the participants and all the students. Won't take much time of you. This is going to be a very learning session, and all the best to all. Thank you. Thank you very much.
Thanks a lot, sir, for your kind words. To extend this program, I really like to introduce our keynote speaker, Dr. Neeta Azad, Professor of Chemistry at University of Delhi for the past over one decade, 2009 present, and has experience of 12 years. She has specialized in physical chemistry, quantum chemistry, spectroscopy, molecular modeling, drug design, application of computers in chemistry, and teaches various courses related to this field. This she has done MPhil, PhD, and her many paper has been published. Her 42nd paper published in Reputed Journalism. So I would like to invite our guest speaker, Dr. Neeta Azad ma'am, to share her knowledge on spectroscopy technique and application. Over to you, ma'am.
Thank you, Insha. I would like to thank Professor Kapkat for his kind words. I would like to thank organizers, Dr. Sukhvinder Singh, Dr. Surbi, for approaching me for this webinar. So, dear participants, I would like to say I'll discuss some of the techniques and kind of spectroscopy you will definitely be benefited with this. So, should we start?
Yes, ma'am.
Okay. Yeah, please can you confirm, is the screen visible to you all?
Yes, ma'am. It is easily visible.
So, today we are going to discuss a few techniques which you already study, students normally study in their courses also. So, we are going to discuss spectroscopic techniques and few of the application which we use in our daily lives and which are normally used in research and science areas basically. So when we think of spectroscopy, the word which strike our mind is what is spectroscopy. As Insha has shortly given the introduction to spectroscopy, but in a chemist point of view, I would like to again give you a brief introduction through a video so that it will be easier for the students to understand what is actually spectroscopy. The most important definition or the most popular definition which you will find in all the books of spectroscopy wherever you study is the study of interaction of matter with radiations. This is the basic definition everyone knows. We have some quantum aspects of spectroscopy also. I'll come to that later. So initially let's see what is actually spectroscopy in visual form. So in the brief introduction, we always say we have electromagnetic radiations which have electric and magnetic fields which are aligned perpendicular to each other. When these radiations, I'm so sorry, just a moment please. So when these radiations interact with the matter, something happens to the matter. And it depends upon what kind of matter we are dealing with. It can be a molecule, it can be an atom. All right. So it depends what kind of wavelength of the radiation is interacting with a particular type of matter. So this is basically the basic idea of spectrochemistry and a simplest definition of spectroscopy. Now comes to the quantum mechanics aspect. In the quantum mechanics definition, I can say spectroscopy is actually the mechanics in action. Or you can say when we actually verify the laws of quantum mechanics experimentally, that study of verifying those laws is known as spectroscopy. So spectroscopy is not independent. Actually, it is dependent on quantum mechanics. So one must understand what is quantum mechanics to understand spectroscopy. So I would just shortly like to tell you a few points about quantum mechanics so that you have an idea how quantum mechanics lead to spectroscopy. So initially you have all studied that we had classical mechanics. Classical mechanics was dependent on Newton's laws of motion, and Newton's laws of motion was applicable to bigger objects. We already know, you must have studied in your primary studies also. So Newtonian mechanics is the branch same. We called it classical mechanics also. So Newton laws of motion was applicable to bigger objects which were uh, very obvious that we can see through our eyes, like bigger bodies, like a stone, a car, or anything which is visible to us, which we can see with the naked eyes. But there comes when we had to deal with microscopic particles like black body radiations, electrons, photons, neutrons, or any other phenomena where the microscopic particles were involved. At that stage, Newton's laws were not applicable because some other results were observed when some experiment was performed. So those experiment was black body radiations, photoelectric effect, Compton's effect. So these were the few phenomena which were not being explained by classical mechanics. So then finally, it was thought that there should be something else behind these microscopic particles so that we can completely explain these phenomena. Then comes quantum mechanics. So quantum mechanics was explained by Einstein and a wave equation was given by Schrodinger. So the idea of quantum mechanics was, when we are dealing with microscopic particles, these microscopic particles have a different kind of nature. They can act like a wave also, and they can act like a particle also. It depends upon the situation or experiment what you are performing. So when it comes to a wave, so it means not only particle behave like waves, it means waves can also have a particle nature. So when we talk about electromagnetic radiations, so Einstein said the energy of electromagnetic radiations is not continuously flowing, but it is coming in the form of some energy packets. And he called those energy packets quantas. So from that word quanta, the quantum mechanics came into play. And those quanta means it can be energy packet of any kind of radiations. But when it comes to light, we call that energy packet as photon. So we are here dealing with photon actually when we are dealing with electromagnetic radiations. Okay. So the 5 basic laws of quantum mechanics was, you have studied, I guess, postulate of quantum mechanics. So I have shortly written them in the form of mathematical equations only. The first quantum mechanics postulate says every particle can be defined by a wave also, and that is, there has to be a mathematical function to define the position of that particle. So that mathematical function is called wave function. And Erwin Schrodinger was the one. I'm so sorry. Erwin Schrodinger was the one who gave this mathematical function psi. He gave it a symbol psi. So psi was the wave function. So he gave this equation which represents the wave. Here E is the energy associated with the particle which have this wave psi. Now, why these quantum mechanical laws are important before going to spectroscopy? Because whatever wavelength we are dealing with in quantum in spectroscopy, whether they are radio waves, they are microwaves, they are IR waves, so we have to form a Schrodinger wave equation for those that wave, and we have to solve the equation so as to get the expression of energy. That is why it is important. So in every spectroscopy, we always formulate a Schrodinger wave equation for our system, whether it is a atom or it is a molecule. We always formulate a Schrodinger wave equation. After formulating Schrodinger wave equation, we try to solve it, and after solving it, we get the energy expression on which the energy level diagrams of spectroscopy are designed. Okay, so this was the first, though we don't need to get into depth of these mathematical calculations, but I have just written over here for your understanding. The first was the wave equation. Second postulate gives the probability of finding any particle within the given region. So when the probability becomes 1, it means that particle is certainly present within those limits, whatever are those limits. Okay, whether in the form of particle or in the form of wave. So psi represents the wave associated with that particle. All right. So particle here means electron, proton, neutrons, microscopic particles. Next was this postulate third, which talks about the operator property. When we deal with the classical mechanics, we talk about various properties like measurable properties, or I must say measurable properties means kinetic energy, potential energy, velocity, moment of inertia, like these properties. So in quantum mechanics, we have operators corresponding to all these properties, and which is given by eigenvalue equation, this third equation. Next one, next postulate says you can calculate the average value of any of these properties using this equation. This is called expectation value equation. And the last one is, if we are dealing with time dependent, we need to define the time also. We will use time dependent Schrodinger's wave equation. So this was the basic of spectroscopy, and quantum mechanics in itself is a vast topic. So before understanding spectroscopy, you must have some idea about the quantum. So that is why I have just introduced it. So next thing is, before studying spectroscopy, it is actually the interaction of radiations and matter, we have already said. So the matter should be characterized in different, parts or different kinds. So here matter is characterized in the form of atoms or molecules. So when we are dealing with the interaction of radiation with atoms, we call it atomic spectroscopy. And when we are dealing with the interaction of radiations with the molecules, we call it molecular spectroscopy, as simple. Okay. Now comes the next part, which is very important, the characterization of radiations. This is very important. This is important because each wavelength of electromagnetic radiations possess different amount of energy. And when they interact with the matter, it will totally depend on the energy of the radiation, what kind of change they will bring to that atom or that molecule. So dividing this entire spectrum into different regions of wavelengths or frequencies is very important. So that is why spectroscopy is divided into different parts. For example, if the wavelength is very high, these are radio waves. So in radio wave region, we have different kind of spectra, like NMR we study in this region, ESR we study in this region. In NMR, nuclear spin is included, and in ESR, electron spin is included. So shifting of spin requires very less energy. We can see from here, if the wavelength is higher, these are the equations you can see. E is equal to hc upon lambda. It means when wavelength is higher, the energy will be lower. Flipping of spin or changing of spin of nucleus or electrons requires very less energy. So we use radio waves in NMR and ESR. Moving on to the higher frequencies or higher energy, as the wavelength decreases and frequency increases, energy increases. So next higher energy waves comes under microwaves. Microwaves are having higher energy than radio waves, but they are much more lesser in other kind of radiations, other kind of wavelengths. So this is again falls in a smaller energy region. So microwaves have that much energy only. They can rotate a molecule. They cannot bring any other change. They cannot make any bond vibrate. They cannot change angle between the atoms or molecules. So they have only that much energy which can help rotate a molecule along different axes wherever they are present. Okay. After microwaves comes slightly higher energy radiations, which are infrared. So infrared, we have near infrared and we have far infrared regions. So infrared region actually is for vibrations. So when the energy is higher than microwaves over here, these radiations has sufficient energy to make bonds between the atoms vibrate. So when they will fall on a molecule, they will make molecule vibrate. So vibrations will occur, and we call it vibrational spectra. It occurs in infrared region. All right. So after this vibrational spectra, so we have NMR, ESR over here, and then microwave rotational spectra. We have vibrational IR spectra. After that comes the visible region. Now, visible spectroscopy is spectroscopy is already very interesting, but I call visible spectroscopy more beautiful. Why beautiful? Because we are able to see the colors here. So whenever any transition, any wavelength is falling in this region, we are able to see the colors, whatever is being emitted by that entity. So this is the most beautiful spectroscopy. All right. And ultraviolet spectroscopy also. In UV spectra, the energy is slightly higher than visible region, but they are not into visible region, so we are not able to see these transitions again. But UV visible spectra go together because they fall in very close range of wavelength. Okay, so these two spectroscopy, UV and visible, have sufficient energy to make the electrons transit from one level to another level. Like the energy is higher, so electrons transition occurs in this region, UV visible region. Okay, after that comes X-rays. X-rays have now even higher energy. So X-rays can cause photoelectric effect. They can cause electron come out of the metal surfaces and so on. So we are going to discuss only these main part of spectroscopy. And if I have time, then I will give you idea about other kind of spectroscopies also. Now moving on to the first part, as we characterize the matter into two parts, atoms and molecules. So first atomic model was given by Bohr. This is very basic and the very beginning of the spectroscopy. So he said electron revolves around the nucleus in different energy levels, and when this this atom gains energy through thermal energy or electrical energy, electron has sufficient energy to jump to the higher energy states, and it can come to the ground states or different lower energy states after releasing a photon. Photon is a so normally in atomic spectroscopy, this photon wavelength falls in visible range, or it can fall in UV, IR, or any of the ranges. So this emits photon. The very basic model is here. The first thing which was studied by Bohr in 1913 was hydrogen spectra. So he took hydrogen lamp and it was connected to a electric source. So hydrogen atoms got energy from that electric source. They went to the higher energy states. When they come back to the lower energy states, they emit some radiations, and those wavelengths pass through prism, and experimentally it was observed that four colorful lines were observed on the photographic plate for the hydrogen spectrum. So it doesn't mean that only four of the radiations, four of the wavelengths are being emitted by hydrogen, but it simply means that only four of the wavelengths are falling in visible region. There may be some other wavelengths also which are not in visible region, so we are not able to see them, but they may be present, or they may be emitted by hydrogen atoms. So we will see it after this. So photographic plate for hydrogen lamp was showing only four lines. You can see here. The same experiment was performed using helium also. For the helium, there were how many? 6 lines were observed. It means 6 wavelengths from the visible spectra was emitted from helium lamp. For the barium, they performed the same experiment again, and there were many lines observed on the photographic plate. And when we do the same experiment with the white light, so all the 7 colors are present here. All the wavelengths are separated by this prism. Okay. So this confirmed that when electron go to higher state, it comes back to the original or ground state after emitting photon, and that photon wavelength can fall in any region of the spectrum. So this is again for hydrogen atom, the 4 lines and their wavelengths. So they all are in visible region. The visible region actually is from 400 to 750, or sometimes 800 we call it. So 400 to 800 nanometers wavelength falls in visible region, and below 400, from 200 to 400 we normally call it falling in UV region. So UV region is not visible to us. Now here comes the again hydrogen. This is for the hydrogen model. The success of this model was we were able to find out the ionization of energy of electron from hydrogen atom. So using this model, this energy equation which was given by Bohr, we calculated the energy of ionization for the electron, which was 13.6 electron volt, and this constant was given a name, Ribberg's constant. Okay, so now we can see here from the different levels when the energy is the electronic coming back to the first level, n is equal to 1, after emitting photon, we call it Lehman series. And if it is coming back to n2, we call it Balmer series. Passion, we have bracket series and Fund series also. So Lehman series falls in UV region. We are not able to say it. All those 4 lines which we have seen in the previous slide, this one. See, these all the electrons are coming back to the second energy level, n is equal to 2, from all other higher energy levels. So these 4 lines are belonging to Balmer series only. In Passion series and above it, all falls in IR region. Again, we are not able to see it. So this was the success of this model, atomic model, that we calculated the ionization energies, and we can use it for further calculations of ionization energy of the atoms with higher number of electrons also. But in atoms which have more number of electrons than hydrogen atom or hydrogen like species, there comes configuration interaction also. When number of electron increases, they cause repulsion to each other. So the factors, the energy terms changes. So term symbols needs to be defined there, and configuration interaction needs to be defined there. So spectrum becomes a bit complicated, but this was the basic of this atomic spectra. So now from this model, we have understood that a particular atomic gas can emit a particular amount of particular wavelength of light. So different lamps I have shown here, they are different in color because when they are connected to electric source, their electron when coming to the ground state are emitting different wavelengths of the photon of different wavelengths. So that is why they are glowing in different colors. So this is the very wide and very important application of this spectra. Now in the applications, this is again, we test metals, they impart a particular a characteristic color to their flame. You must have done your labs also. From the color of the flame, you can have idea which metal is present in your sample. So this is an application of atomic spectra. Again, in fireworks or crackers, if you want a particular color to be shown in the cracker, you put a particular kind of atom or ion, you will get that particular color because of atomic spectroscopy. And you must have seen glowing signboards also on the shops and markets. This is another examples of this kind of spectroscopy. So this was the atomic spectra, a basic idea, and a few applications in our daily life. Now I will move on to the molecular spectra. So molecular spectra is very important and it has very wide applications. Why? Because whenever we do some research in the lab or wherever, we always form a molecular compound, whether it is a medicinal compound or anything, any salt or anything, we form molecules. So we are dealing with molecules more than atoms in our labs. So that is why this spectroscopy is important from research point of view. So whenever you have formed a compound, you will note down its NMR spectra, you will note down its IR spectra, and you will be able to find out what functional group and what atoms, what molecules, how many kind of protons are present in that particular molecule. So you can come up with a conclusion for your research. So this that's why molecular spectroscopy holds a very it is of prime importance. The main spectroscopies are in this field. There are many, but I have not listed all of them because I don't think we have that much time so that I can discuss all of them. But a few very important parts are: first is NMR, nuclear magnetic resonance spectroscopy. I have already told you, NMR deals with the spin change of the nucleus, right? So NMR is okay, it happens in radio frequency region. ESR again dealing with the spin of the electron. It is again happening in the radio frequency region. They are less smaller energy regions. The wavelength of radio waves is very high and the energy is low. After that comes microwave spectroscopy. So rotational spectra occurs in microwave region where the energy is slightly higher than radio frequencies and it is lower than IR and visible frequency, right? And IR spectra is the one which is vibrational spectroscopy. So we study them individually, but these two go side by side. So whenever you record vibrational spectra, it is always accompanied by rotational spectra. We will see how. I will show you through a small video how it happens. Next is UV visible spectroscopy. In UV visible spectroscopy, what happens? They require more energy. And in this region, electronic transitions happens. So I have written here change of electronic distribution. It means electronic transitions between different energy levels will happen. Let's see how the electronic, vibrational, and rotational levels are interrelated to each other, and how we need what amount of energy we need for these kind of transitions. Let's see. So when radiations interact with a molecule, it gives rise to a spectrum where we have, see, this is the energy level diagram for the various electronic, vibrational, and rotational energy levels. So from this diagram, we can understand electronic energy transitions needs very large amount of energy. All right. And each electronic level is confined with a number of vibrational levels. It means vibrational levels require less energy than electronic transitions. Electronic transitions. Levels also. So each vibrational level is again confined with a number of rotational levels also. So rotational levels are very small and they need very less amount of energy for the transitions. Okay, so this is one important point. Another important point is, see, the rotational levels are not equally spaced. When you are moving towards the higher energy terms, the gap between the rotational levels is increasing. I'll tell you later how they are related to our bands or frequency bands, what we receive when we note down the rotational spectra. And in vibrational levels, they are equally spaced from each other. Similarly, for electronic levels, they are equally spaced, equally away from each other. So electronic transitions need more energy, and lower wavelength, higher frequency they need. Rotational transitions need lesser energy. If you see in this spectrum, which was shown here, I'll show you how they fall in different regions. So the two important types are pure rotational spectra, pure vibrational spectra, and electronic band spectra. We call it electronic band spectra because electronic transitions are always accompanied by vibrational and rotational transitions. So they are not sharp peaks, rather than they show a kind of bands. Okay. Rotational and vibrational spectra, we study them individually, but they are again not independent. Vibrational and rotational spectra, they come together, and we study the combined form of these two in IR. So for the rotational spectra, I have already told you we need less energy. And when photon is falling on the molecule, it makes it rotate only and not vibrate, only rotate. So only for the rotations, and these are small energy radiations, they fall in microwave region and far infrared region. For next vibrational spectra or vibrational rotational spectra, a little more energy is needed. They are accompanied by rotations, and the bonds also vibrate. So it is vibrating as well as rotating. So vibrational rotational spectra, and this is observed in near infrared region of the spectrum. Vibrational transitions are happening here. In next one, electronic band, we need really high amount of energy for the electronic transitions to the different levels. So electronic transitions are accompanied by rotations and vibrations as well. So we have electronic band. These are rotation levels, rotation transitions are taking place. So this was the basic idea. Now we will study one by one how rotational energies are calculated and what are the applications of what information we can draw from rotational spectra. After that, how vibrational energies are calculated and how we interpret from its spectra, and after that, electronic spectra. Okay, wait. Yeah. So the first one is rotational spectra, which falls in microwave and far infrared region. Before we understand the spectra of any atom or any molecule, we must know what was the basic of that calculations. So in quantum mechanics, I already told you spectroscopy is not independent, but it is dependent on quantum mechanics only. So quantum mechanics used a few laws of classical mechanics and then calculated the various amounts, various expressions. So understand one thing, that in quantum mechanics, we always, the first step is to formulate a Schrodinger wave equation for your system. You must take a system which is closer to your practical system. So we have taken over here a rigid rotator. Rigid rotator means two masses are connected to each other. In this picture, you can see two masses are connected to each other and they are rotating around the axis which is passing through the center of mass. Rigid means the bond is rigid. The distance is not changing. So this was the simplest model for the rotations. So quantum mechanics used this model to calculate the energies of a rotating molecule. All right. So after solving the Schrodinger's wave equation, we have got an energy expression. This energy expression you get when you solve Schrodinger's wave equation. And from this equation, we can see J is a constant which is appearing, which we have never heard about before. So this J is the rotational quantum number. Now rotational quantum number is quantum numbers are those which defines how the transitions will occur between different energy levels. So this is a rotational quantum number, which is very important. Second thing is this constant was given another name, which was rotation constant, capital B. So here we have rotational constant and rotational quantum number. Now these two, rotational constant is very important. Whenever we record any spectra, the position of the band will give us the value of B. The position of the band give us the value of B. From this value of B, we can calculate the bond distance, because B is in its expression is having bond distance. So it is easier for us if we note down the spectra, rotational spectra of a molecule, we can find out the bond distance of that molecule. Bond lengths can be calculated. This is very important application of rotational spectra. Okay, so the spectras are normally, you must have seen, are noted down and mentioned in wave number terms. So when you calculate the wave number from energy expression, the wave number will be given by 2b j plus 1 centimeter inverse. Now here, when you calculate from this expression the difference between uh, sorry, the difference between various energy levels, you can just subtract this E1 from E2 when you want to calculate the difference between any two consecutive energy levels. So you will find out the energy gap is increasing. So this energy level diagram comes from quantum mechanics. So it was derived from the quantum mechanics, and we finally used it while doing experiment in spectroscopy. And here the selection rule is delta J is equal to plus minus 1. It means the transition which is acceptable can be either directly to the above level, immediate above level, or immediate below level to it. So transition has to be between the consecutive energy levels. And when these bands are observed, uh, the another important observation was these rotational bands were equally spaced or at equidistant from each other. This is another very important thing, because when we calculate the difference of the two closely spaced bands, we can easily know these two bands are 2b apart. See, this is 0, 2b, next one is at 4b, 6b, and 8b. So if you calculate the difference, you will get, if you find out the difference of the two peaks, two wave numbers you are getting in the spectrum, you can easily find out the value of B, and you can further calculate many parameters about that molecule. So this was the application part of this, and mathematical basics of rotational spectra also. So this slide only shows a few important mathematical expressions which are important to draw information from the spectra. If you know energy is related to quantum number, moment of inertia, and it is related to angular momentum, you can calculate various parameters very easily. So it is all about calculating, extracting information from the spectra, what you observe from your experiments. Another very important application of this is isotopic substitution. Let's first see what is isotopic substitution. We assume that we have a rotational spectra of CO. His C is here, C12. Okay, so in CO, we have bands which are equally spaced on the spectrum, 2b, 4b, 6b, 8b, 10b, 12b, centimeter inverse. These are wave numbers in terms of wave numbers. Okay, so if we do not have any data for C13O, we want to calculate the bond length of this molecule. What we do? We simply note down the spectra. We will make the substitution. We note down the spectra of this molecule, rotational spectra, and compare with the rotational spectra of C12. So here is the pictorial comparison. When we have substitute a heavier atom in the place of a lighter atom, C12, what happens? The energy levels are coming closer. They have come closer, and the frequency bands has shifted towards the lower frequency. This is the consequence of substitution. Now, what information we can draw from the mathematical calculations is, we have the value of B rotational constant for C12O. We can have same expression for C13O. We can divide these two B's rotational constant, first one and after substitution, and we can calculate the bond length of this CO molecule. So this is another application and aspect which is very simple and which makes calculations very easy for us. Now this model was when the rigid rotator is rotating harmonically. Harmonically means there is no disturbance in its rotations and it is continuous. What happens if it is not rotating harmonically? We have non-rigid rotator, which is okay. This is again non-rigid rotator, which is again rotating harmonically. Non-rigid means the bond is not fixed anymore. The bond is changing. It may be increasing or decreasing. So we have another constant added to the equation, which is dj square j plus 1 whole square. This is distortion constant or centrifugal distortion constant. The expression is given by this. It is complicated, no need to worry about it, but we must understand there are some term which has been added to this energy expression. So this was for harmonic. Again, this is non-rigid rotator, but again this is harmonically rotating. What happens if it is non-rigid and it is enharmonically rotating? It means there will be some other terms defining those enharmonicity will be added to this energy expression. So this energy expression becomes more and more complicated and lengthier. So this was the simplest model, rigid rotator, which we discussed for the rotational spectra. One of the very important application we use in our daily lives is microwaves, which we use in our kitchen every day. So how this is helpful? Microwaves are lower in energy. They makes the water molecules which is present in the food items to go into higher energy state. When they come back to the lower energy state, they emit energy and they make our food hot. So this is very important and very simple phenomena which we use in our kitchens. But the important thing is we are always said that don't come in contact with microwaves. Don't put your hand inside when it is working, because our body is also having water. Our body's water molecules can get affected by these radiations and cause harm to us. So we must be very careful while dealing with microwaves. Now we are moving towards the basic aspects of vibrational spectroscopy. So in vibrational spectra, I have already told you, it happens in IR region of the electromagnetic radiations. Now IR spectra comes from, now, again, quantum mechanics plays important role in calculating the energy expressions. But before applying that quantum mechanics, we have taken a model of ball and spring from classical mechanics itself. So we have, in classical mechanics, we have harmonic oscillator. Either we deal with a pendulum or we deal with a spring. When it is set up into vibrations, they will harmonically oscillate. So we have taken this model of spring and balls because we can easily compare our atoms with these balls and spring with the bond length. So bonds are also flexible. They can compress, they can be stretched. So that is why we have taken this model. And we already know this kind of curve is observed when the potential energy and kinetic energy changes in between. At certain point, potential energy becomes zero. At certain points, kinetic energy becomes zero. And in between, they both play role. They both exist together. Okay. So this is potential energy expression for this harmonic oscillator, half kz square, or sometimes we write half kx square. X is the distance from the mean position. So using this expression again, before solving for this energy, we again have to formulate a Schrodinger wave equation. I am again telling you, spectroscopy is totally dependent on, it is a part of molecular mechanics only. It is an application part of molecular mechanics. So unless you solve Schrodinger wave equation for the different system, you will not get any energy expression. You will not be able to know how far the energy levels are lying from each other in a particular system. So to understand that, we always have to form a Schrodinger wave equation. But in vibrational spectra, for the vibrating molecule, Schrodinger's wave equation again becomes a bit complicated. So we simplify it by putting various simplified expressions or some applying approximations and all. So finally, after doing so much of calculations and work, we finally get a simplified energy expression, which is mentioned here. En is equal to n plus 1 h bar omega. This kind of expression you get. So here small n is the vibrational quantum number. Vibrational quantum number starts from 0 and its value 0, 1, 2 and so on. So when you calculate from this expression difference between any two consecutive energy levels, it is coming out to be equal. So I initially told you the vibration levels are equally spaced in harmonic oscillator. they are equally spaced. It depends on it. This idea we have got from the calculation from quantum mechanics. So they are equally spaced. But rotational were not equally spaced. We have seen from its energy expression also, they were not equally spaced. So this way we get a spectra for harmonic oscillator. Now on the right hand side, I have mentioned this this kind of energy plot, potential energy versus the distance from the nucleus. So this is for enharmonic oscillator. When enharmonicity is lost, it is not, because this is a realistic problem. See, this harmonic oscillator is a ideal problem. What we think has to be there when it is behaving ideally. But in nature, we don't have any ideal things. We have to deal with enharmonic oscillators only. So when the molecules are behaving like enharmonic oscillators, the energy levels are not equally spaced. Though I have not mentioned here the energy expression, but here again a few terms will be added. And when you find out the difference between two energy levels, the energy difference will keep on decreasing when you move towards the higher energy levels for enharmonic oscillator. Okay, so initially from 0 to till few energy levels, we say this model follow quantum mechanics. After that, the gap decreases so much that the energy levels are continuous. It means beyond this level, they will follow classical mechanics. Because in classical mechanics, we call the energy is continuously flowing. But in quantum mechanics, we call the energy is coming in form of packets. So whenever the energy levels are discrete or present at a distance, this is followed by quantum mechanics, and the above part it will be followed by classical mechanics. So this is the point where this is dissociation energy. This is the minimum energy required to dissociate a molecule. If you stretch a molecule beyond this limit, beyond this distance, say this is 5, the molecule will be broken. So it dissociates. So this is the simple mathematical phenomena behind the vibrations. Now, what are the application and what information we draw from this is, the most important thing is normal modes of vibration. It is very important for any kind of molecule to know how many modes of vibrations will be present. How many vibrations modes means how many frequencies or peaks we will observe in our IR spectrum. This is the information which we get. But it is not important that all the modes of vibrations are IR active. There is a condition for it. To be IR active, there should be changing dipole moment. So if the dipole moment is not changing through any vibration during any bending or stretching vibrations, that will not be shown in your spectrum. So we will got only those frequencies which are IR active. So, we only discuss about the IR active modes. So this is the formula which is again easy to derive. 3n minus 5. This is the formula to be given for the linear molecules. So this gives the number of vibrational modes in any linear molecule. 3n minus 6 is the number of vibrational mode in any non-linear molecule. These are generalized formulas. I hope you know the mathematical calculation behind it. Okay, I can explain it. If a molecule have 3n degrees of freedom, 3 is the coordinates for each atom, when at the position of an atom defined by 3n coordinates. So if there are n atoms, we have 3n coordinates to define that molecule. It means there is 3n degrees of freedom. So out of 3n, we have 3 translational degrees of freedom and 3 rotational. So total, when you subtract translational plus rotational from total, you will get vibrational modes. So that is why we are making it 3n minus 5, because linear molecule can rotate only along 2 axes. It is lying parallel to the one. So rotation around this axis doesn't mean anything. It will still be the same molecule. So rotating around x-axis and y-axis, x-axis and z-axis make a sense. So for a linear molecule, we will have 3 and minus 5. For a non-linear molecule, we will have 3 and minus 6 molecules. So 6 modes, sorry. So here for HCl, you can calculate normal modes of vibration. We have n is equal to 2 over here. 3 into 2 minus 5 is equal to 1. So it has only one stretching mode, which is stretching. There is no bending because angle is not present here. So only one stretching is observed in the spectrum. Now comes the second example, which is CO2. Now CO2 and H2O both have 3 number of atoms, but the difference is CO2 is a linear molecule and H2O is a non-linear molecule. So CO2, for the CO2, the vibrational modes will be calculated like 3 and minus 5. N is 3 over here. So normal modes of vibration will be 6 minus 5 is equal to 4 vibrational modes. So I have already told you 4 vibrational mode need not necessarily be present on the spectrum. Out of 4, how many vibrational modes are accompanied with change in dipole moment? Those will be reflected on the IR spectra. Otherwise, other rest of the modes will not be mentioned there. They will be called IR inactive modes. For H2O, we have again 3 number, but the equation is 3 into 3 minus 6 because it is a non-linear molecule. So 9 minus 6 is 3 vibrational mode. So let's see how CO2 have different modes of vibration in the form of a video. So here you can see, first is the symmetric stretching for CO2, in which both the two carbon atoms, both the oxygen atoms are going apart and closer all together. So this is this stretching mode is not accompanied by any change in dipole moment. So this is IR inactive mode, the first one. In second one, the oxygens are moving closer and away from the atom in this manner. So they are accompanied by change in dipole moment. So this mode is asymmetric stretching, and this is IR active mode. Another one is scissoring. So this is in plane scissoring and this is out of plane scissoring. But if you observe both of them closely, they are same scissoring. These two symmetrical bendings are identical. So these bendings will be reflected only in single peak. So let's see, when we noted down the spectra, IR spectra of this CO2 molecule, what was observed. So we have seen only 2 frequencies, 2 peaks downward. One is related to anti-symmetric stretching and second one is corresponding to bending. These both the bendings out of plane and in plane, both are same. So this happens. Now comes the application of IR spectroscopy. So IR spectroscopy is the most important spectroscopy and it has wide application in research. IR spectroscopy and NMR. You must have already heard, whenever you prepare a compound in the lab, a new compound, a drug or whatever, you always tend to note down its IR spectra and take its NMR. These two spectra are more than enough to find out which compound had been formed. So why it is important? In IR spectroscopy, we have different kind of, it is divided into different regions. So we have group frequencies and we have fingerprint regions. So group frequencies means for a particular functional group like aldehyde group or alcohol group, C double bond O, HCO. So different kind of groups, you have different kind of frequencies. So already know this kind of group is present in a compound, then we will observe a peak at this frequency. So we call it group frequencies. Similarly for the bonds also, when there is bond stretching, so we have fingerprint regions. So C bond C, C double bond O, or CH bond, or whatever bonds are present, they will always have a signature frequency to them. We call them fingerprint region. So in the fingerprint region, you observe a particular kind of frequency. So when you note down the IR spectra of any compound, you know what functional groups are present in this compound, and you know what kind of bonds are present. So these two informations are more than enough to design your structure or what you are expecting, to get an idea about the compound what you have prepared in your lab. So this is very important application. Identification of a substance. Second is identification, means if you have a substance in the lab and there it is not labeled, you don't know what compound is lying in this container or bottle, you simply take IR spectra of it, and you can match with the spectra of any compounds which are listed in your book, and you will easily get to know, because every compound have a different IR spectra. No two compounds will have same spectra, IR spectra at all. So this is again very important for the identification of substances. Again, studying the progress of the reaction. If you are if a reaction is undergoing and you want to find out at what stage a reaction presently is, what you can do is you simply take the reaction mixture. You have to freeze the that reaction mixture at that particular point first. You freeze that reaction so that you can have an idea where we have proceeded till. So you take small sample of that reaction mixture, you take its IR spectra. If you get the frequencies of a particular bond length in fingerprint region, you can easily find out what bonds are missing which were there in the reactant, and what new bonds have been formed in the product, and what are still to be formed. So you can have an idea about at what stage your reaction is. So in this aspect, this is very important. Detection of impurities, again very important. If you have a known compound and you want to find out whether some impurity is present or not, you already know the IR spectra of that compound, you again take the spectra of that impure compound. So after comparing the spectra of the pure compound and impure compound, if there are some additional peak in the impure compounds, you will easily know some other things are also present along with this original compound. So detection or for impurities, for the detection of impurities, this plays again a very important role. So these were the two very important spectras, the rotational and vibrational spectras. So I have already told rotational spectra is the one which require very less energy, and they are always accompanied by vibrational spectra. So whenever we record an IR spectra, it is rotational plus vibrational spectra. Okay. So okay, so rotational plus vibrational spectra, if you want to find out the energy gap or design the energy level diagram, you simply take the energy expression for rotational spectra plus energy expression for vibrational spectra. So mathematical treatment is very easy. You need not do it again and again for the system. You have already done it for rotational spectra individually. You have done it for vibrational spectra individually. You can take the two expressions and then combine them and can find out the energy gaps or whatever information you want to draw. And you can draw the same information what we have discussed in the two individual spectra from the combined spectra also. For example, I have taken an example of rotational vibrational spectra of DCl, deuterium chloride. So another important factor which comes here in rotational vibrational spectra is P branches and R branches. So when we talk about this rotational quantum number delta J, its selection rule was delta J has to be equal to plus minus 1. So when delta J is equal to minus 1 means the transition is taking place between two vibrational levels. See, this is vibrational plus rotational spectra. It means vibrational transitions are there and also rotational transitions in between are there. So from first vibrational level, I take J is equal to 1. J is equal to 1 rotational level is going to J is equal to 0 of second vibration level. This is ground and this is first excited state, first vibration level. So here J was 1 and here J is equal to 0. It means higher minus lower, 0 minus 1 will be minus 1. So all the transitions which happens in this region delta J is equal to minus 1, they are called P branches, and P branches fall in the towards the lower wave number side. See, over here from 0 till the wave number is increasing. So towards lower wave number side we have P branches, towards higher wave number side we have R branches, and Q branch is the one where delta J is equal to 0. It means same, the transition is happening from J is equal to 0 to J is equal to 0 of next vibration level, or J is equal to 1 to J is equal to 1 of next vibration level. So rotational level is not changing into Q branches. So for Q branch we don't observe any peak, there is a band gap in between. So from this spectrum, we have an idea about how far these peaks are lying. We already know these are lying 2B apart. It means when I take the difference of these two frequencies of these two peaks, I can compare it with 2B, calculate the value of capital B, which was rotational constant, and from B you can draw the information. You can find out the bond distance of DCl, you can find out the molecular masses of these two atoms, or any unknown atoms if you have. So this is again important application of rotational vibrational spectrum. Now after rotational vibrational spectra, we move on to the visible spectroscopy. I already told you in the beginning, visible spectroscopy is the most beautiful spectroscopy. Why beautiful? Because it is visible to our eyes. We can observe colors through our eyes, and whatever we can see colorful, it is already beautiful. So I have taken, for example, I have just taken these few pictures of moon. These all are the picture of moon at different places of, they are captured from different places on earth on different occasions. It means here how the spectroscopy is observed here, the radiations which are coming from the sun are interacting with moon, which is matter, and we are observing some different colors at different time. It means different wavelengths are reaching our eyes, our retinas, in different intensity at different times. So that is why we are observing different colors. So this is another beautiful example. One more form of this spectroscopy is a rainbow. Again, the interaction of the radiations with water molecules. So water molecules are matter here. They act like prism, and they split all the 7 colors of the visible region, and this rainbow is formed. This is another visible form of visible spectroscopy in our daily lives. These were the 2 examples. There are many more, but these are the 2. So I find it easier to understand the things when we relate it with our daily lives. It is easier to understand, and it develops one's interest also to understand the phenomena, why it is happening. Now, both UV and visible spectroscopy, these both are explained by Lambert-Swirr law. Though in visible region we see the colors, in UV region we are not able to see. So UV region is 200 nanometers to 400 nanometers of wavelength, and visible region is from 400 to 800 nanometers of region. So even if we are not able to see the radiation in UV region, but when you note it down through UV spectrophotometer, you will observe the wavelengths, you will observe the frequencies on the spectrum. So it is not important whether they are visible to us or not, but Beer-Lambert's law is the law which defines these 2 spectroscopy. With the help of these, we can find out various parameters of our given compounds. For example, if the compound is color, let's talk about in terms of visible spectroscopy first. If I am dealing with a colored compound, which we normally deal with, student must have seen copper sulfate solution in the lab, which is sky blue in color. You must have seen KMNO4 solution, which is purple. Crystal violet is also violet in color. Second is K2CR2O7, which is orangish color, right? So whenever you have a colorful solution, you can always use this formula A is equal to epsilon Cl to calculate the concentration of such solutions. So this formula was given by Lamberts and Beers. And again, this A is equal to A I naught upon I. A here is the absorbance. And what is absorbance? We have a source of light, a monochromator, and a light is incidenting on the mixture. See, this is cuvette or cell, or whatever container you are taking, in which a colored solution is lying. So when the colored solution is lying over here, I naught intensity of the light is being incident on it. Some will be absorbed, other will be transmitted through the solution, and detector will detect the transmitted light. On the basis of that, it will calculate the absorbance. So transmittance, to define absorbance, we must know transmittance. Transmittance is the fraction of light which has been passed through the solution without being absorbed. This is the important and basic definition. Transmittance, what is transmittance? Transmittance is the light, a fraction of light which has been transmitted through the solution and which is the transmitted light is reaching the detector. So absorbance is actually, see here, I upon I naught, absorbance is log of I naught upon I, so log of 1 upon T. So absorbance will be equal to log of 1 upon T. So if you know the transmittance, you can again calculate the value of concentration. Or in our spectrophotometers, or if you are dealing with colorimeter also, there is an option. You can either calculate absorbance directly, or you can calculate transmittance directly. So absorbance is more convenient to note down. So normally in the lab, what we do is we take a colored solution, and before taking its absorbance, we must also know in which solvent it has been prepared. Because solvent will be its reference. Solvent should be such which do not have any absorbance of its own. So we always take blank solution as the solvent in which the colored solution is prepared. So after using the blank solution and the colored solution, we put both the solution in our spectrophotometer and note down its absorbance. It's very easy. If you are doing it experimentally in the lab, it's very easy. Note down absorbance and you can find out easily the concentration. Epsilon is the molar absorptivity coefficient, which is specific to a color. You already have its values for different colored solutions. So you can always use the value of epsilon for your respective solution, whatever you are using. And L is here the path length. Path length means the width of this column. Whatever apparatus you are using, whatever container you are using, the path length. Normally we use cuvette, and which is 1 centimeter wide in the labs. So this is standard cuvette. So using this law, when you compare this equation with y is equal to mx plus c, you can plot a graph between absorbance and some known concentrations of your solution. So graphically also you can find out the concentration of any unknown solution. So this was the mathematical concept behind dealing with UV and visible spectroscopy. Again, as you know, UV visible radiations have enough energy to make electronic transitions. So in this region, electronic transitions occur. Again, it depends on the compounds, what kind of electrons are present in that particular compound. If you are having alkenes, you have sigma star transitions, sigma electrons are present there. If you have carbonyls, these kind of transitions are possible. If you have unsaturated compounds, so pi to pi star transitions are possible. So again, from electronic transition bands, we can draw this information, what kind of band we are observing at what kind of frequency. You know that this kind of functional group is present in that particular compound. So again, electronic spectra is again helpful in finding out what kind of functional groups are present, what kind of electrons you are dealing with in this system. So this is the application of UV and visible spectroscopy. So when you take multiple spectra, like you have taken UV visible spectra, you have taken IR spectra of a compound, and you are taking NMR. So you can combine all these all these information from various spectra to know what is your original compound if you are dealing with a unknown compound, or you can confirm also which compound is this. So application of UV visible spectroscopy, one I have already told you. Another very important application is, these are the experiments which we normally perform in our labs, in undergraduate and postgraduate labs. So another important application is, if you want to find out if you want to find out about a compound, whether it is present in this or not, or the concentration of the compound which is present in any solution. Say it is not colored. Okay. So for example, if I have a solution of mohr salt, it has iron in it, but it is not colored. I want to find out the concentration of iron in that solution. What I can do is, I can make use of UV visible spectroscopy. In fact, how? I can add something to it which can combine with iron and form a colored complex. Right? Normally we do it. We use 110 phenolphthalein as indicator into the iron solution. It combined with iron, Fe2 plus. It gives a brownish orange color to the solution. So after noting down the absorbance, I can make use of this graph and find out the concentration of iron in solution. So the application is very simple. Whenever you know a compound can be converted to a colorful mixture, you can always make use of visible spectroscopy to find out the concentration of that compound. Similarly, is applicable for indicators also. We have in our lab phenolphthalein indicator, but phenolphthalein is not colorful, as you see, but it gives color when it is present in the base. So when if I take NaOH and add few drops of phenolphthalein, it will turn pink. So if here also I am able to convert that uncolored compound into some colorful compound, so I can again easily note down its absorbance and find out its concentration, or I can find out its indicator constant also. We have methods, mathematical calculation for the same. So these are few experiments. These are simple experiments, but making use of these experiments, you can do use of this spectroscopy for other compounds. For example, in your lab, you are preparing a medicine or a drug or something like that. So you must have studied its properties. You want to know what is the concentration, or what concentration has to be optimized, so you can make use of it, change it into color compound, and make use of UV visible spectroscopy. So we normally do, you can study the kinetics of any reaction. In this, we study iodination of acetone. We know iodine will be faded, the color will be fading when the reaction go towards forward, or any other reaction you can take in which color is enhancing or color is decreasing. Whatever can be the condition, you can take the solution at different point of time, note down its absorbance, and you can find out the proceeding of the reaction or the concentration of the product at any particular time, how much product have been formed. So this is another use of it. And these are again initial two simple experiments. You can always determine the concentration of any color compound. You can also find out when the more than two color compounds are present all together, you can find out their individual concentrations also, but there are some conditions. The two colored solutes which are present in a solvent should be non-reactive. They should not interfere with each other. They should not make any chemical changes to each other, and they should be comfortable with the same solvent. This is important. It should be comfortable with the same solvent, means they should not have any kind of arrangements, rearrangements, or change in color in same solvent. So this is the condition. Or you can find out the concentrations of more than even two or three, four, five compounds in any colored mixture. So these were the few uses. So I stop here. I guess I try to include NMR also, but NMR in itself is a very wide, subject. So we need more time for that. So for today, I stop with this. And for the references, you can consult these books which are on spectroscopy, which are very important, very good books for you. The videos which I have included in my presentation, I have given the links here. You can always make use of it, and you can watch them on YouTube as per your convenience. I have recorded a few lectures for my students also on quantum. If you want to study or understand the basics of quantum, you can visit my channel also. You can write to me if you find any difficulty in understanding spectroscopy or quantum chemistry with Dr. Neeta, Neeta at @gmail.com, or on my official ID, Neeta Azad @arsd.du.ac.in. Thank you.
Thank you a lot, Azad ma'am, for enlightening words on spectroscopy technique and application. It's really an insightful and exhaustive session for us. We are grateful to you, ma'am, and we have some queries and some questions. I request you to kindly resolve them. So it's time for QA session.
Yeah, sure.
Over to you, sir.
Good afternoon, Dr. Neeta. Good afternoon, Dr. Neeta.
Good afternoon, sir.
There are some queries from the students, and I'll ask you one by one. And the first question is that, what's the differences among the quantum mechanics, classical mechanics, and the molecular mechanics?
Actually, classical mechanics I have introduced. It is based on Newton's laws of motion, and it is for bigger objects only.
Okay.
Whatever you can see with your naked eyes is a part of classical mechanics. In quantum mechanics, we have microscopic particles. When you are dealing with electrons, when you are dealing with protons, neutrons, atoms, which we cannot see with our eyes, but so Newton's laws was not applicable on quantum mechanical particles. So quantum mechanics deal with microscopic particles, classical mechanics deal with macroscopic particle. Now comes molecular mechanics. Molecule means a entity which is related to chemistry. So when you apply quantum mechanics to chemistry, it becomes molecular mechanics. As simple as that.
Okay. Okay. Thank you, ma'am. The next question is what is the differences between the spectroscopy and spectrophotometry?
Yeah, spectrophotometry and spectroscopy, or I can say spectrophotometry is a part of spectroscopy. Spectroscopy is a branch which deals with the interaction of matter with radiations, but spectrophotometry is the one where photon of energy, the light is involved, white light is involved.
Okay. Now the next question is, which type of spectroscopy is most commonly used in the biomedical analysis?
I already told you, whenever we design any molecule, whether it is medicinal use, it is for chemical use, we always note down IR spectra of it and NMR spectra. These are the most two important, widely used spectras, and these are not that easily available also. A very few institutes in India has those instruments so that we can note down these spectras. So
Okay.
IR and NMR are the most important spectras.
The most commonly used spectroscopy in R&D sector?
Again, the same. Yeah.
What are the instrumental advancement in the spectroscopy?
Instrumental advancements like the basic idea of spectroscopy is always same. You take a source, you pass it the radiations through monochromator, then you pass it through slits, or you make it to pass through your sample. The basic idea of main chemistry is same, But when you are doing a particular kind of spectroscopy, you use different source of different wavelengths. So instrumentation is almost same. Whenever you study spectroscopy, it is always discussed in the first chapter that this is the setup for the spectroscopy. So setup is almost same. Sometimes according to the spectroscopy, you have to arrange the sources of different radiations. Like if you are doing something with x-rays, x-rays are very harmful. They are ionizing radiations, so the body should not come in its contact. So safety point of view should be different for different kind of radiations you are using.
So now the next question is that, can we measure contact angle by IR?
Contact angle by IR. Contact angle, I have not think in that ways, because you get wave number, you get number of modes, bending modes, and when you know the bending vibrations, so I think yes, once you know the bending angle, you will be able to find out it. I'm not sure, though I cannot provide you the exact equation or anything so that you can calculate, but I think it is.
It's sure, ma'am. Okay, thank you. Now next is what is the differences between the IR active and IR inactive?
IR active are those modes which have changing dipole moments. If dipole moment is not there, the positive and negative charge separation is not there. It means that mode is not possible to interact with the radiations, because radiation is moving in a way positive and negative manner. So there should be change in dipole moment. So all those modes which are accompanied by change in dipole moment can interact with IR radiations and can give IR spectra, and those which are not giving any kind of change in dipole moment will not be IR active.
Okay, thank you, ma'am. The next question is what are the basics type of the spectroscopy? You have mentioned there are a number of types of the spectroscopy, NMR, IR, FTIR, and a lot of. But what are the basics types of the spectroscopy that the other types have been evolved from it?
These whatever I have discussed are actually the basis of spectroscopy: the rotational, vibrational, and electronic. This is the basics. After that, it comes electronic spin resonance electroscopy. You have NMR, you have Moss-Boyer spectroscopy. There are many types of, but they all have evolved from this. You study Raman spectra also, that depends upon scattering, right? So this was the basic, where you needed minimum energy, and from minimum to higher energies we move.
Okay, ma'am. Thank you. The next question is that what is how could we relate the quantum mechanics to spectroscopy? As up to the knowledge what I have, that in the recent times that most of the research is going on the quantum mechanics, and a number of patents have been occurred by the Chinese government also. So the quantum mechanics is rising. But what's the role of the quantum mechanics in the improvement of the spectroscopy? Whether they have any type of the association that the spectroscopy is used.
I would just like to explain this in very layman's language, very simple language. We are not able to write dictation until unless we know ABC, right? So until unless you know quantum, you will not be able to derive the energy equations, and further you will not be able to decide what is the placement of energy levels in spectra. So from the quantum mechanics, we always formulate a Schrodinger's wave equation for any system we want to study. After solving Schrodinger wave equation, you get wave function and you get energy expression. These two are very important parts. So from wave function, we draw different kind of information. But from energy expression, we are able to find out what kind of energy level arrangement will be there in any kind of molecule. So that ways.
Okay. Let's thank you, ma'am.
Yeah, thank you so much.
Okay. Finally, respected Dr. Neeta Azad, Assistant Professor, and Professor Gurudat Kakad from the Career Point University, all the staff, deans, and HODs. I deem it a great honor to express my sincere thanks to all of you for your presence in the webinar. And first of all, my big thanks to Dr. Neeta Azad for their valuable address on the spectroscopy. Madam, as you have keenly discussed every aspect of the spectroscopy, from the types of spectroscopy and their applications. And moreover, what are the modern trends and the instrumental advancement in the field of the spectroscopy. So once again, thank you all. I would like to express my thanks to Professor Gurudat Kakkar for their provide an opportunity to organize such an event. I am also very grateful to all our HODs, staff members for their efforts to conduct this webinar. And finally, my sincere thanks to all the participants, including professionals, teachers, scholars, and the students from all parts of the India for their presence and make this event successful. So once again, thanks to all. Thank you.
Thank you, sir. Thanks a lot, Neeta, ma'am. Above all, thank you everyone watching this session. This is Inshara on behalf of Career Point University. Have a good day.
Thank you.